Hello everybody, this is Mr. Koker again. This is Module 2 of Chem 2, Chem 106 Parkland Dual Credit. We are looking at matter and energy. In our 10th edition, this would be Chapter 2, but in the 12th and 13th edition, this would be Chapter 3. So as you're doing your work on your class supplement, you might want to use Chapter 2 instead of Chapter 3 for this, if you're working out of the 10th edition textbook. So what is matter? Could you name some different examples of matter? Matter is anything that makes up a substance. It always occupies space and has mass. Matter is composed of atoms, and atoms bond together to form molecules. So anything that makes up a substance occupies space or has volume, and anything that has mass, anything made of atoms or atoms bonded together to make molecules, these would be examples of matter. So matter is all around us. If we use the classification system, we first learned this in Chem 1, starting with matter, we go through the dichotomous key and ask ourselves, what are the two main kinds of matter? Well, matter that can be simplified and broken down by physical means are called mixtures. Mixtures are composed of two or more different kinds of atoms or molecules. They're physically mixed, not chemically combined. But if matter cannot be broken down physically, we say that it is pure substances, composed of only one type of atom or one type of molecule, and has a fixed composition. So if it does have elements, then those elements are chemically combined. Different kinds of atoms are chemically combined to make molecules. Pure substances can be broken into two categories. The types of pure substances that cannot be further broken down into simpler substances, even by chemical means, are called elements, but compounds can be broken down chemically into two or more elements. These elements will always be in a fixed, definite proportion. They are chemically combined, but they're combined in a particular ratio, like H2O is a compound. Where would we go to find the elements? Well, of course, we would go to the periodic table of the elements. And that's where we would find examples of all the elements. If you go to the internet, you can find lots of examples of periodic tables. You can even find some interactive periodic tables where you can click on the elements and see actual samples. Wolfram, a local software company in Champaign, has many samples of elements, and they have the actual elements themselves, and they have excellent photographs of those elements. So if you ever wanted to know what the element titanium looked like, or what the element bromine looked like, you could see pictures of these on the internet posted there by the Wolfram software company from Champaign, Illinois. Now, elements combine together in certain fixed ratios or whole number ratios of atoms to make compounds. Could you name some compounds? Maybe you're thinking of water or carbon dioxide or something slightly more complex like glucose. Now if we go over to the other side and talk about mixtures, mixtures have two types: homogeneous mixtures, where the mixture is so well mixed it appears to be blended into one material. Its composition is the same throughout the sample. You think about adding color to paint to color it. There's a point at which you have blended the color into the paint so well that it's all one color. That's what we kind of mean by homogeneous. Heterogeneous composition will vary throughout the sample, and so you will see different regions of a heterogeneous mixture having different properties and different composition. So in summary, matter is anything that makes up a substance occupies space and has mass, is composed of atoms, or atoms bonded together to make molecules. There are two kinds of matter, pure substances and mixtures. Pure substances have only one type of atom or molecule and have a fixed composition, whereas mixtures are composed of two or more different types of atoms or molecules and are physically mixed, not chemically mixed. Pure substances can be classified as either elements, substances that cannot be further broken down into simpler substances, even chemically, or compounds, substances made up of two or more elements. And if you chemically decompose a compound, you would break it down into its elements. The elements in a compound are in fixed, definite proportions, certain ratios of atoms. The elements in a compound are chemically combined, giving them new properties. Mixtures can be broken into homogeneous and heterogeneous types. In homogeneous, the blending is so well that they are the same, the composition is the same throughout the sample. A synonym for homogeneous mixture is solution. So if you think of saltwater solution, the salt mixes throughout the water in a homogeneous mixture. A heterogeneous mixture, the composition will vary throughout the sample, and so typically you can see the parts of a heterogeneous mixture. So if we look at some examples of mixtures, homogeneous mixtures that are the same throughout and heterogeneous mixtures are not the same throughout. So typically, if we think of a bar of soap, probably in most cases we're looking at a homogeneous mixture. Although certain brands of soap do have color stripes in them. If you think of, say, Irish Spring or Coast soap, maybe you can see the greenish stripes or the bluish stripes. That would indicate that it's not homogeneous. Toothpaste is typically homogeneous unless you get the kind that has different types. Maybe the fresh breath gel and the cavity fighting fluoride part are two different parts, and they come out of the tube, and you can see that it's actually a heterogeneous mixture. Many of our beverages are homogeneous unless if you think of maybe orange juice with pulp, that would actually be heterogeneous because the pulp is a different, is not the same throughout, not the same as a liquid. Muffin, typically going to be heterogeneous. You're going to see little bits of raisin or something in the muffin. This rubber eraser appears to be homogeneous. It appears to be the same throughout. Sand. Many types of sand are actually heterogeneous mixtures, and you can see different materials in the sand. Maybe you see white grains and black grains in the sand. Beverages. Beverages are typically homogeneous mixtures. Pizza, obviously a heterogeneous mixture. Different regions are, the bread crust, the cheese, the sauce. There's different regions. It's not the same throughout. These gumballs of different colors, obviously heterogeneous. Soil in a flower bed, it would be a heterogeneous mixture because you can see maybe a grain of sand, maybe a bit of clay, maybe a bit of organic matter. It's a mixture. So matter can be broken down into many different types. Copper, it would be an example of an element, only one type of atom. Water would be a compound. It's got hydrogen and oxygen atoms, but notice they're in a fixed proportion. Brass is a mixture. Brass is a mixture of copper and zinc. The copper and zinc are blended very well, and you cannot see the copper and zinc separately. It's a homogeneous mixture. It's a solution of metals. It's an alloy. A piece of copper sitting on the bottom of some water, say some pennies in a glass of water, that would be a heterogeneous mixture. You have the water region and the copper region. Okay, so we're looking at states of matter next. Solid, liquid, and gas. Solids, when you look at their shape, have definite shape, whereas liquids will mold themselves to the shape of whatever container they're in. Gases also take the shape of their container. The volume of a solid is a definite volume. Solids cannot be squeezed into smaller volumes, or they don't expand much, maybe a little bit when heated, but generally we say they have a definite volume. Similarly with liquids, although a gas can expand or contract depending on the volume of its container. In a solid, the particles are fixed in position. They're very close together. That's why we can't squeeze a solid and make it smaller. Liquids are more random, but they have very similar closeness to the particles that solids do. Liquids and solids generally have similar densities. In a gas, the particles are far apart and randomly organized as they move about inside the container. Particles have very strong interaction between the particles, strong enough to hold them in fixed positions. Liquids have relatively strong interactions, strong enough to hold them close together. Gases, the particles are so far apart, typically 1,000 times more distance between them than in a liquid or solid, so gases have essentially no interaction between the individual particles. Solid particles do move in a vibratory motion. Liquids particles can move, and they can also slide past each other, and allows for diffusion to occur. Gases move very quickly. They move in straight lines until they bump into another gas particle or the wall of the container, and then they bounce off and reflect. So examples of solids: ice, table salt, iron. These would be examples of solids. Liquids would be water, oil, or vinegar. Gases, water in the vapor state. So we've got solid ice, liquid water, and water in the vapor state. All three can exist on Earth. Helium and air, another would be two more examples of gases. When we describe matter, we describe its properties, its characteristics. There are characteristics of matter that we can use to tell substances apart. There are physical properties, properties that a substance can display without changing composition. I can measure the density of a material, and I don't have to change it into a new material to do so, so I would call density a physical property. There are also chemical properties, properties that you can only observe by changing the substance. For example, paper is flammable. Flammability is a chemical property. How can I tell paper is flammable? I have to burn the paper. Well, burning paper causes it to undergo a change in composition. So properties that are a description of how something chemically reacts are called chemical properties. Physical changes can be used to separate mixtures. Now, physical change would not cause a change in the composition of the material. So I can take mixtures made up of more than one kind of material, could be a homogeneous mixture, could be a heterogeneous mixture, and I can separate the parts from each other using various physical changes. Since components have different physical properties, I can take advantage of that and use various physical changes. You would be able to separate a mixture of blood from the red blood cells would be able to be separated from the plasma. If I separate by boiling point, I take advantage of the two different boiling points of the parts in the mixture. I can vaporize the lowest temperature boiling portion of the liquid and allow that vapor to collect in a condenser and turn back into from a gas back into a liquid. I can keep the condenser cool using maybe water from the faucet to keep it cool. The condensation of the vapors turns it back into a liquid. Gravity pulls it into the second container, and I'm able to separate the lower boiling component from the higher boiling component. Can also separate by particle size. Particles that have a large size won't pass through the filter paper. So by filtration, I can separate large chunks of solid from a liquid that might pass through the filter paper. The part that goes through the filter paper is called the filtrate. The solid that gets caught on the filter paper is called the filtrand. So that was our discussion of matter. Let's move to our discussion of energy now. In science, we talk about two kinds of energy, potential and kinetic. Potential is energy of position, and kinetic is energy of motion. Energy is defined as the ability to do work. So our parachutist has parachuted in on the right side of the slide here, and when that parachutist is up in the air, he has potential energy, energy of position. That energy is converting to kinetic energy as he falls. The farther he falls, the faster he moves, and so kinetic energy is energy of motion. Potential energy can convert to potential energy can convert to kinetic energy. All right, little learning check. Let's quiz you on what you know so far. Here we see the water behind the Hoover Dam. It's much higher than the water on this side of the Hoover Dam in the picture, and so the water on the behind the Hoover Dam has potential energy, energy of position, just like the parachutist being at a high distance gave him the ability to move and gain kinetic energy as he falls. As this water falls from its high position into the low position of the water on the closest side of the Hoover Dam here, the water can actually, its movement can actually generate electricity, and so you can have a hydroelectric dam. Heat is a form of energy. Heat is transferred from a hot object to a cold object. It's one of the most common forms of energy. When the particles in a hot substance have more kinetic energy than the particles in a cold substance, when they come in contact with them, the collisions between the hot particles will speed up the particles in the cold, and so as a result the hot object gets cooler and the cold object gets warmer. The transfer of energy from hot to cold is called heat. How do we measure energy? Well, the International System Unit of Energy is called the joule, capital J. Joules are not much energy. It's a small energy unit, so very often we will use the kilojoule instead of the joule. Of course, a kilojoule is 1,000 joules. Because of that, we can convert from one to the other. We can say 1 kilojoule for every 1,000 joules, or 1,000 joules for every 1 kilojoule. Another unit of energy sometimes used in chemistry is called the calorie. Now when you see the word calorie, you want to look for whether or not the calorie is spelled with a big C or a little c. If it's spelled with a little c, then little c calorie is the amount of energy required to raise a gram of water 1 degree Celsius. Big C calorie is actually a food calorie. So if you think about counting calories in your diet, that's actually a big C calorie, and it's 1,000 little c calories. It's a kilocalorie, actually. It's still called a calorie, but by spelling it with a big C, we are designating it as a kilocalorie, or 1,000 times larger than the calorie that is the energy required to raise 1 gram of water 1 degree Celsius. Now, little c calorie is actually equal to 4.184 joules. You don't need to memorize that. We will always give it if you need it in a problem. So these would be the conversion factors. 1 calorie over 4.184 joules, or 4.184 joules over 1 calorie. So let's look at some problems here. Convert 284 joules to kilojoules. Convert 17 big C calories to little c calories. Convert 27.3 little c calories to joules. And convert 8,638.6 little c calories to kilojoules. Let's remind ourselves what our conversion factors are. 1 little c calorie is 4.184 joules. Using 284 joules times 1 kilojoule for every 1,000 joules, we get 0.284 kilojoules. One small misprint here. Kilojoules should be a lowercase k, actually. For kilo, we use a lowercase k, not a capital K. If we convert the 17 calories to little c calories, we should actually multiply by 1,000. So 17 big C calorie is 17,000 little c calories. Converting little c calories to joules requires us to multiply by 4.184 joules per little c calorie. And then converting 8,638.6 little c calories to kilojoules actually requires 2 steps. First of all, we'll convert little c calories to joules, and then joules to kilojoules, and we'll end up with 36.144 kilojoules. Now the conversion factors are assumed to have infinite sig figs, and so the conversion factors do not control the sig figs in the final answer. Only the starting unit and starting number will determine sig figs in the final answer. If we look at temperature, temperature is a measure of the average kinetic energy of the particles in a substance. For example, boiling water on the Fahrenheit scale is 212 degrees Fahrenheit. On the Celsius scale, it's 100 degrees Celsius. And on the Kelvin scale, it's 373 kelvins. Normal body temperature in Fahrenheit is 98.6. In Celsius it's 37, and in kelvins it's 310. Freezing point of water is 32 degrees Fahrenheit, 0 degrees Celsius, and 273 kelvins. Now if we look mathematically here, kelvins basically is the Celsius value plus 273. If we look at how Celsius and Fahrenheit compare, between 0 and 100 there's 100 Celsius degrees, but between 32 and 212 there's 180 Fahrenheit degrees. So that ratio of 180 to 100, or a ratio of 1.8, can be used for converting Fahrenheit and Celsius. So some temperature conversions. If you want to know the Fahrenheit temperature, you can take 1.8 times the Celsius temperature and add 32. If you want to know the Celsius temperature, you should first subtract 32 from the Fahrenheit temperature and then divide the answer by 1.8. If you want to know the Kelvin temperature, you should add 273 to the Celsius temperature. Using those conversion factors, let's see if we can find the body temperature in Fahrenheit of a patient with a temperature of 37 degrees Celsius. Fahrenheit temperature is 1.8 times the Celsius temperature plus 32. So 1.8 times 37 plus 32 is a healthy 98.6 degrees Fahrenheit. Okay, another learning check. When the body's core temperature reaches 301 degrees Kelvin, it is considered severe hypothermia. So what temperature would 301 degrees Kelvin be in Celsius? And then what would it be in Fahrenheit? Of course, Kelvin is Celsius plus 273, so Celsius would be Kelvin minus 273. 301 minus 273, you would be down to 28 degrees Celsius. 1.8 times 28 plus 32 is 82 degrees Fahrenheit. Yes, that would be severe hypothermia if your body temperature got down to 82 degrees Fahrenheit. course, the sig figs on this, 1.8 times 28 equals 50.4, but you actually only have 2 sig figs, so it rounds to 50, and 50 plus 32 is 82. Now if we go back to heat, heat being the energy associated with the motion of particles, another way of defining heat is the energy transferred from a hot object to a cold object. The symbol for heat that we use in chemistry is Q. We measure it in either joules or calories. The equation we use to describe the amount of heat needed to raise the temperature of a substance is we say that Q, heat, equals M, mass, times C, specific heat, times the change in temperature. Q equal mc delta T. M being mass in grams, C being the specific heat. Sometimes specific heat is represented as capital S, capital H, or maybe as capital C. Delta meaning change in, and T meaning temperature. So delta T means change in temperature. Let's see if we can apply that equation. How much heat in calories are required to heat 250 grams of water from 15 degrees Celsius to 25 degrees Celsius? Well, Q equals mc delta T. So the mass of the water is 250 grams. We said earlier it takes 1 little c calorie to raise the temperature of a gram of water 1 degree Celsius. So we'll make that the specific heat of water, 1 calorie per gram degree Celsius. And then if we look at our delta T, our change in temperature, we're going to 25 from 15, so 25 minus 15 is 10. 250 times 1 times 10 is 2,500. Grams cancels out, degrees Celsius cancels out. All we're left with is a unit of heat of 2,500 calories. So a little more about what we call specific heat, sometimes represented as capital C, sometimes as capital SH. Specific heat, the amount of heat required to raise the temperature of 1 gram of substance 1 degree Celsius. If we manipulate the heat formula, we can actually find the specific heat of a material by dividing the heat by the grams and by the change in temperature. So that's just a reorganization of Q equal mc delta T. There's 3 possible units. Actually, there are 3 units in specific heat. There's the joules or the calories on top, there's the grams on bottom, and there's degrees Celsius also on bottom. Let's try this one. A pot weighing 260 grams increases in temperature from 72 degrees Celsius to 114 degrees Celsius. You put 21,143 joules of heat in. What is the specific heat of the metal that makes up the pot? Remember, specific heat can be found by dividing heat by mass and by change in temperature. So 21,143 joules of heat divided by a 260 gram pot, and also divided by 114 minus 72. Ends up being 1.9 joules per gram per degree Celsius with 2 sig figs. Now if we think about the big C calories that we use to measure the energy in food, using information from the nutrition guide on the side of a container of food, you can actually calculate the total calories of food in that sample based on the different nutrients that make up the sample. The 3 main food types that give us energy when we eat food are carbohydrates, fats or lipids, and proteins. So the carbohydrates are going to give you 4 kilocalories, or 4 big C calories per gram. Fats give you 9 big C calories, or kilocalories per gram. And proteins, like carbohydrates, give you 4 kilocalories per gram. If we use that in a problem, we could calculate the calories, notice big C calories, kilocalories, in 2 tablespoons of peanut butter. So if the serving size is 2 tablespoons and a serving size of peanut butter is known to contain 6 grams of carbohydrates, 16 grams of fat, and 7 grams of protein, how many total calories would be in 2 tablespoons of peanut butter? Starting with the carbohydrate, 6 grams times 4 kilocalories per gram gives us 24 kilocalories from the carbohydrates. 16 grams of fat times 9 kilocalories per gram would give us 144 kilocalories from fat. And 7 grams of protein times 4 kilocalories per gram would give us 28 kilocalories from protein. Adding them together, 24 plus 144 plus 28 is 196 kilocalories from 2 tablespoons of peanut butter. Let's think about the energy changes when substances change states. We'll use water as an example here. Here we see different forms of water that might occur in the wintertime. The water in the snow is frozen. It's solid water. If it's a puddle of water, then it's liquid. If it's water vapor in the atmosphere, then it's a gas. If we talk about the names of the different state changes, when solid goes to liquid, when the snowman turns into liquid water, he is melting. When the liquid evaporates to form a gas, it's called vaporization. If gaseous water in the air turns into snowflakes in the upper atmosphere, or maybe frost on your windshield, gaseous water turning into solid is called deposition. If we go the other way around, if the snowman turns into gaseous water, that's called sublimation. If the gaseous water turns into a liquid, that's called condensation, which can occur in a cloud. If the liquid water turns into solid ice, then that's called freezing. Now the 3 conversions here, deposition, freezing, and condensation, that are in dark blue are examples of heat being released. Heat being released when bonds are formed. So when a gas turns into a solid or a gas turns into a liquid, hydrogen bonds are forming between the water molecules and heat is being released. Bonds are forming. B-A-R-F, bonds are forming, barf comes out, heat is released. On the other hand, the red arrows represent examples where heat is absorbed. The bonding is weaker in a liquid than a solid, so melting requires the breaking of some bonds. Bonds are breaking, heat goes in. Barb, a barbed wire, the barb points into the skin. When the liquid turns into a gas, hydrogen bonds are broken, that's called vaporization. Likewise, when a solid turns into a gas, it's called sublimation, and that also breaks bonds. Heat is absorbed. The heat absorbed during melting, in order to separate the particles from the solid and make them into a liquid, is called heat diffusion. For water, that heat diffusion is 80 calories per gram of ice. 80 calories equals 1 gram of ice, and so 80 calories per gram can be used as a conversion factor. Some substances can go straight from solid to gas, like dry ice can go from solid to gas. Or iodine can go from solid iodine to purple iodine vapors. This is called sublimation. Evaporation is what happens when molecules go from the liquid to the gas phase. at the boiling point, where you have enough vapor pressure generated by the gas phase to overcome air pressure, when the vapor pressure equals air pressure, then the molecules will have enough energy to go from the liquid state to the gas phase in the form of bubbles, and that's called boiling point. Condensation is just the reverse of evaporation. When gas molecules are cooled, typically by contacting a cold solid object like the cold mirror in the bathroom when you take a hot shower and the water turns into liquid on the mirror, that is called condensation. The molecules have lost energy to go back to the liquid phase from the gas phase. Heat of vaporization is the heat that is used to turn a liquid into a gas, and so when a liquid has sufficient energy that every molecule is almost ready to become a gas, that's, in other words, you're at the boiling point. The energy required to make the liquid into a gas is called heat of vaporization, because you have to break some bonds, some hydrogen bonding between the molecules to turn it into a gas. Now, we said earlier water has a heat of fusion of 80 calories per gram. It has a heat of vaporization of 540 calories per gram, which can also be used as a conversion factor. So how much energy is required to convert 205 grams of liquid water into water vapor? We would want to use the conversion factor of 540 calories per gram. 205 times 540 is 110,700 little c calories. Now, because this is heat absorbed, we give it a positive sign. If it was being released, we would give it a negative sign. If we look at these graphs here, we call these heating and cooling curves. We can see that on the left, as heat is added and temperature rises, solid material will raise in temperature until it reaches its melting point. At its melting point, its temperature will level off and remain at the melting point until all the solid has turned into liquid. Then, once it's all liquid, the liquid can warm up to a higher temperature until it gets up to its boiling point. As it boils, it remains at the same temperature, the boiling point, until it's all boiled. And then if you wanted to further heat the gas formed from the boiled liquid, then the vapor could be heated to a higher temperature. Where we see the temperature going up, we see a change in the kinetic energy of the molecules, where we see the temperature constant, but the solid turning into liquid or the liquid turning into gas, we are actually seeing changes in potential energy. The cooling curve on the right shows what would happen if steam at 140 degrees Celsius was cooled to 100 degrees Celsius, where it could condense into liquid water. Then the liquid water could be collected and cooled down to 0 Celsius. At 0 Celsius it will start freezing into ice. Once it's all frozen, it could go from 0 down to -20, -30, whatever low temperature you cooled the ice down to. On the left we see what would happen if heat was added to a cold solid. On the right we see what would happen if heat was removed from a hot gas.